Hello and welcome to another video presentation courtesy of the University of North Texas Physics Department with the assistance of the Physics Demo Room. My name is Corey Nook and today's demonstration is going to be talking about the moment of inertia, and we're going to be looking at that compared to several different objects. But now the first thing is, what is the moment of inertia? Why do we have this concept? Well, this concept was brought about because before we've always talked about translational motion, at which point we don't consider an object really rotating, but just moving about in terms of the XY plane. But now we can actually have objects where not only are they moving linearly, they're also going to rotate. And they'll have some angular acceleration or angular velocity with that. Well, with this, we might say, well, momentum talks about an object's resistance to change, its inertia. Well, the moment of inertia is the rotational analog of an object's resistance to rotate about an axis. Well, with this, we can think about there's several different ways of looking at how objects rotate. So, for example, a book that most of you might have referenced at home or might have one handy is longer than it is wide. Now, we can think about three different ways of rotating this book. We can think about it if this is the x-axis, towards you is the y-axis, and out of the book, or out of the plane, is the z-axis. I can rotate this book about the z-axis, I can rotate this book about the y-axis, and I can also rotate this book about the x-axis. Now, with this book, this is actually a unique case that if I rotate about the z-axis, plain and simple, it won't actually have any abnormal motion to it other than it's just going to continue rotating. The same way if I just flip it about the y-axis. The x-axis actually has a unique property to where not only will this book go and rotate about one axis, it'll also flip. So it'll actually go over two axes. So this is how I'm going to flip it. As you can see, the person's right here. We'll see if we can. Now the person's on the other side. It did a rotation in the air. This is a unique property because of the shape and the mass distribution of this book and the rotational axis. So now we can say is, well, since we have this moment of inertia, we talked about momentum, but we also have energy as well. So with these different objects, they each have their own different moment of inertia based on their shape. So we can look at some examples here off the board. We have a thin hoop, which is this object right here. As you can see, the radius, the inner and outer diameter are very close to each other. That moment of inertia, when it's just rolling down the hill, is mr squared. Now, if I had a solid cylinder, such as this object, that moment of inertia is 1/2 mr squared. Now finally, or not finally, but the next object, let's say we have a cylinder, but it has a hole in the middle. What we can do is we can look at the moment of inertia is 1/2 the mass of that object times the quantity of the radius of the inner diameter squared plus the radius of the outer diameter squared. Most of the time, this is usually denoted as ID for a subscript for inner diameter and OD as a subscript for outer diameter. This is a useful thing to learn because this is also very common when it talks to machine parts and trying to find home improvement tools. They'll talk about the inner diameter and outer diameter, but they'll label it usually as an ID and an OD. And finally, the last object we'll be looking at is a uniform sphere that its moment of inertia is 2/5 mr squared. Now this is really just looking at how does the mass distribute about the rotation axis, which is the radius. So in this case, we'll say, well, I've got these different objects, but how do I apply this moment of inertia? And that has to go with the concept of conservation of energy. So beforehand, whenever we talked about energy, it was always, let's say, the potential energy and the kinetic energy before the situation starts has to equal the same, has to equal a potential energy, a kinetic energy after the events take place. Well, now if an object's allowed to rotate, we have an additional term for the initial and final situations, which is 1/2 the moment of inertia times its angular velocity squared. Now, most of the times the angular velocity can be related to its tangential velocity. But now you have this additional energy term for both the before and after. So now, if you have a bigger moment of inertia, it's going to take more energy to get that object rotating than it will with a smaller moment of inertia. So a smaller moment of inertia means that the potential energy can transfer more to translational energy than rotational energy. So that means with these objects, we want the smallest number for its moment of inertia. So from these above, the smallest number would actually be the 2/5 mr squared, or a solid sphere. The sphere should go first. Well, then the second one that should be occurring should be the solid cylinder, followed by the hollow cylinder, finally by the thin hoop. So it's going to take more energy because it's going to take more energy is going to be put into rotation and less into the translation because the moment of inertia is bigger. So now let's just take two of these objects and let's just see which one reaches the bottom first. So they're going to be very close to each other. I'm going to have them lined up, and now we let them go. They don't hit each other. Okay, apparently my board is not level. But as you can see, even though I left them both go first, that the sphere will actually reach the bottom first. I know this is not perfect because I believe my sphere is a little bit off. But now let's do the same concept of a solid cylinder and the ring. Same concept. The solid cylinder got to the end of the ramp before the ring, or before the thin hoop. It's because more energy had to be converted to rotate this than our solid cylinder. So this might be counterintuitive, going, hey, this is thinner, why wouldn't this move forward? It's because it's how much energy, or it's of how the mass is distributed about this ring requires more energy to rotate it than it does for the solid cylinder. Well, that is it for our little video presentation for this demonstration. Thank you for watching and have a wonderful day.